right, well, hello. Um, so, as always, I am Nathan. I am most of the way done a PhD in chemistry, and welcome to my place where I get to be a big nerd and talk about things that I think are fun. Um, so, usually I start this off by talking about whatever I feel like. If there's something usually academically related that I will just talk about for a bit, but I don't have anything like that today. So we're just going to get right into working through a problem set. Um, and today, finals are very much upon us. One of my tutoring students requested that I go through a problem set that they're working on, just for studying for their final. It's for just an intro chem class. So yeah, without any further ado, we'll just start going through that. And let me get as uncomfortable as possible. Alright. So, I just want to see if I can. Okay, give me 1 minute to just change a little something in there, and then we're good. Okay, sorry. Don't worry about that. You just I'm the man behind the curtain as far as you're concerned. Don't worry about it. Okay, so starting with question 2 here, because question 1 was a bunch of fill in the blank stuff, and I could talk about that, but there was a lot of them, and perhaps if there's time and brain space, when I get to the end of these questions, we'll get back to it. But we'll see how I'm doing by then. So we'll start with so complete the following table. So we have we're given in all of these cases the value z, and what z is referring to here is the number of protons that are in the corresponding element, which directly corresponds to the atomic number on the periodic table. So Z, the element with 4 protons in it is just this one here, beryllium, and it's really, really small. I'll see if I can get over there and zoom in for you. So this here is this inconveniently small atomic number. Just trying to get that. Sorry, also not your concern. Okay. So the element with z equals 4 is indeed beryllium. E, and so it's also asking the charge of the most commonly formed ion. Now, for the charge of the most commonly formed ion, it's going to conform to, at least in the first 3 rows of the periodic table, this always conforms to a noble gas configuration, or a full octet kind of configuration of electrons in the valence shell. And generally, these will occur such that, so like for group 1 that have, like in the case of sodium, sodium has a full 1s orbital, that's just the first 2 core electrons, and then a full energy second electron shell plus 1 electron for sodium. So the quickest and easiest way for sodium to get to a noble gas configuration would be to lose one electron. Uh, and it's very, very good at doing this. Sodium holds very, very loosely to its one valence electron that's in the 3s shell. Uh, and so going down the row of the periodic table, elements in group 2 tend to form a +2 charge because they have to go 1 and then 2 to get to its noble gas configuration. And so things like boron, it's in group 13 or group 3 if you ignore the transition metals. So it has 3 valence electrons. It tends to occur in the +3 oxidation state so that it can go 1, 2, 3 and get to its noble gas configuration. Carbon can kind of go either way because it's got 4 valence electrons. It can go to a +4 oxidation state, so it's 1, 2, 3, and 4 to a noble gas configuration, or it can be in the -4 state and go 1, 2, 3, 4 to its noble gas configuration corresponding to neon. And then nitrogen tends to be -3, oxygen tends to be -2, and fluorine tends to be -1, all to get to the noble gas configuration of neon. So when we're talking about, I should mention, if we're talking about groups 1 and 2 in particular, these effectively always will be found in the +1 and +2. Okay, so we're not using the oxidation state terminology for this. So they will tend to take on a +1 charge for the group 1 elements, or +2 charge for the group 2 elements, because that gets them to their noble gas configuration. So beryllium, being from group 2, is going to adopt a +2 charge. If you ever see beryllium in a different charge state, a +1 or 0, don't touch it. It's going to be very reactive, and beryllium is quite toxic, actually. Anyways, that's neither here nor there. Okay, so next one, Z, or a proton count of 21, puts it at, yeah, there we go, scandium. So scandium, the closest, most accessible noble gas configuration of scandium will be from having a charge of +3, which, now that I'm looking at it, they've already specified that the most common charge is +3. So I guess we'll just kind of not worry about that. But essentially that gets it to a noble gas configuration as well. You lose 1, 2, and 3 electrons, and it takes on the electron configuration of argon. Z of 28 is going to be nickel. And yeah, so that's just this guy here. And the charge the most commonly formed ion is +2, and that is given. It's given because they do not expect anybody in introductory chemistry to be able to assert the most common charge for the ion of transition metals, because there's usually more than one. Because scandium has, like, the second most common charge on scandium is -1, because that puts it into the electron configuration of calcium, which means it's got a 1s2, 2s2, whoops, 2, 2p6, 3s2 configuration for scandium plus. So the reason that this is somewhat stable is that this 3s electron shell is full, and that it has 2 electrons in it is somewhat stabilizing. It's not great. It's much better energetically for scandium to be in the 3 plus oxidation state, because that's a noble gas configuration, whereas this is not. But it's still, more stable than its neutral form, and it. Trying to think if it has any reduced forms or negative charge forms. Very rarely, let's call it. I don't like making blanket statements like this never occupies a negative oxidation state, because it probably could, but generally it will not. Okay, so let's keep going. Okay, so Z of 34 puts us at selenium. So selenium is in group 6 or group 16, depending how you count it. Oh, that's a nice S. There we go. Let's try that again. There we go. So that is the element selenium, and its most commonly charged ion. Charged or most commonly... I cannot say that phrase, and I'm going to stop trying. So, the charge that selenium normally adopts is -2. And that's because it's in the same group as oxygen. And so if selenium is to gain 2 electrons, you'll end up at krypton, which is its closest noble gas configuration. Because gaining 2 electrons is a whole heck of a lot more energetically favorable than losing 6 of them. Very, very different propositions between those two. So it's far more, by far the most common to have selenium in the -2 state. And the next one over is 35, and that's going to be bromine. And bromine, as with all of the halogens, is most stable in the -1 state. Alright. Okay, so complete the following table. Okay, so now we're getting into things when we start talking about nuclear chemistry. So this is where we start to concern ourselves very heavily with isotopes. I'm sorry, my nose is terribly itchy. Give me a moment. There we go. Okay. So, when we're doing nuclear chemistry, we always include the number of neutrons with the, well, in the particular isotope that we're talking about. And so the way that this symbol format is laid out is, so it's so let's break it down over here. BI1, 86, and 83. So yeah, on the periodic table, there's several numbers, and there's no one way to organize them, because up here we have the atomic number. God, can't even draw a line. There we go. Much better. So we have the atomic number, which is the number of protons in the nucleus. And then we have this down here. So I'll get closer so you can see. So this 22.99. This is the mass number of sodium. And so that is the weighted average of. So the mass number here is the average mass of naturally occurring isotopes. That is a lot of text to spell out. Please bear with me. isotopes. It's messy, but it's fine. Okay, so the mass number is the average mass of naturally occurring isotopes for this element. So that requires a little bit more explanation. So this is saying that if you take a completely average sample of sodium in nature, it will come out to weighing 22.99 mass units, where protons and neutrons are almost exactly equal to 1. So sodium is not the best choice to make when you're trying to talk about the average mass number, or average mass of isotopes, because it's almost exactly 23. Doesn't give me a whole lot to talk about. Something like magnesium at 24.3 is easier to talk about, so I'm going to do that instead. Whoop. There we go. Okay, so now we're talking about magnesium for the mass number. So what this means is that most of the magnesium, now I'm debating if I'm going to use magnesium, because I don't know off the top of my head the stable isotopes. So what we're going to do, I got an idea. No, I just want this. None of this is working. Okay. So we're going to go over to chlorine. And I'm going to explain chlorine because that's the one that I do know the isotopes off the top of my head. So, talking about mass number, average mass of the naturally occurring isotopes. So the naturally occurring isotopes of chlorine are chlorine 35 and chlorine 37. And so there's a bunch of chlorine that has a total mass of 35, and there's some chlorine that has a total mass of 37. So how does it get to a mass of 35 and 37? Well, if we take the atomic number, which again, the atomic number is the number of protons. So for chlorine, that's 17. So there are 17 protons in the nucleus of chlorine. So to get to a total mass of 35, we go 35, that's a nice 3. Now let's move this over here so you can actually see what I'm doing. So 35 minus 17 is 18. So for the isotope chlorine 35, there are 17 protons and 18 neutrons in the nucleus. We don't tend to really count the number of electrons because the mass of electrons is very, very small. Electrons weigh about 1/1000th of what protons and neutrons weigh. But protons and neutrons are almost exactly the same mass as each other. So to get the number of neutrons, we take the mass number of the isotope, not this mass number, this number. We take the mass of this single isotope, subtract the number of protons that are in the nucleus, and we get the number of neutrons that are in the nucleus. So now, where this ties into the mass number on the periodic table. So if you take a sample of chlorine from out in the wild, you will have approximately 75% of the chlorine being chlorine 35. So each chlorine nucleus has a mass number of about 35. 25%, give or take, of the chlorine that you collect will have a mass number of 37 because there's 2 more neutrons in the chlorine 37 isotope. So if you take the weighted average of these, 35 times 0.75 plus 37, let's move over again, times 0.25 divided by 2. I wonder if that actually works out, because I might have the formula wrong here, but let's try. Forget the plus 2. Ignore that. Boop, boop, boop. So yeah, you get about 35.5. This is going to be a little bit different because the ratio is not exactly 75 to 25. I'm sure I've got that a bit wrong, but more or less like so this is how it is. So the mass that's reported on the table is the average mass of a sample of chlorine with the abundance of the naturally occurring isotopes just weighted by the abundance of the naturally occurring isotopes. That's the one. Okay. So if we go back here, I actually guess I'm done with that. So right, so we were explaining this. So, the notation that we use when we're dealing with nuclear chemistry is always going to specify the isotope that we're working with, because we're not concerned with what is the natural abundance of each of these stable isotopes. So we're not concerned with what isotopes are stable or naturally occurring or whatever. We're just concerned with what isotope is this one in particular. And so to figure out what we're working with, so this would be called like bismuth 186, because the 83 here is the atomic number. Which is, again, the number of protons in the nucleus. And the 186 number is the total mass. So the 186 is the mass of the number of protons plus the number of neutrons. So it's going to be protons plus neutrons. That's real nice. That is messy as hell. That's fine. We're going to go with it. So, then what we can do with this is we can find the number of neutrons in the isotope by going 186 minus 83 equals 103, unless I'm very much deceived. So 103 N, or 103 neutrons. And so this can matter when we're talking about the stability of a nucleus, because we'll see in just a minute here, because part of this question deals with, is this isotope stable? And I'll show you the resource that we use for that. But so talking about this notation again, the 83 is the atomic number. It's the number of protons in the nucleus of the element that we're looking at. And that, for any given element, the atomic number will never change. It cannot, because if it has a different number of protons, it is a different element. It is the number of protons in a nucleus that defines the identity of an element. And there's no other measure for that. So like hydrogen always has one proton. It can have 0 neutrons and be just hydrogen. It can have 1 neutron and be deuterium or hydrogen 2. Or it can have 2 neutrons, and it can be tritium, which is a hydrogen 3 nucleus. Bismuth, super don't know those off the top of my head. But again, things like chlorine can be chlorine 35, which has 17 protons and 18 neutrons, or it can be chlorine 37, which has also 17 protons but 20 neutrons. Yeah. So yeah, for those, I'll just write those down for a bit of a visual aid, because you can have 35 Cl 17, or you can have 37 Cl 17. So these are the options for the naturally occurring chlorine isotopes. So it can be 35 or 37. And when we're doing nuclear chemistry, we're dealing with exactly one of these at a time. Whereas if we're doing things just on the periodic table with normal natural abundances, then we do the mass number, which is the weighted average of the isotopes. Okay, so excuse me. Okay, so here we're talking about bismuth 186. So again, the Z is the number of protons, which is the atomic number, and that is 83. And N is the number of neutrons, and that's going to be 103. And let's do this one too, and then I'll show you the resource that I'm talking about. So, titanium, 60. 22. Okay, so in this, the 22 again is the atomic number, the number of protons, and the total mass of this element is 60. So the number of protons is 22, and then the number of neutrons must be 38. Okay. Alright, so with that, I'm going to go all the way to the bottom of this problem set, because there's a data sheet, and if I'd thought ahead, I probably would have moved this up to where it would be useful, but that's just not how we're going to do things right now. Okay, so we had BI 186 and 83, and we had TI 22 and 60. Gross. Alrighty. So, this graph here is called the band of stability, and so this has Z on the x-axis, so the number of protons in an element is on the x-axis, and the number of neutrons in that element is on the y-axis. And this kind of fuzzy band here is like all of the known isotopes of that are all of the known isotopes that are stable for all of the various elements that we have access to. Because once you get past 100, it gets a little bit silly. So the band of stability is saying, like, with this proportion of protons and neutrons, you can generally expect a nucleus to be stable along this band. And so if it is outside of the band of stability, then it is going to undergo some spontaneous decay, a radioactive decay of some sort, in order to get to the band of stability. So if, for example, you had something that was well, let's actually take these examples, and we'll just see where they fall on this graph. So if we had something that is atomic number 83, so it's about here, and neutrons was 103, which is right about there. I'd say, yeah, okay. All right, so I know I can do a line on here, can't I? Yes, very good. Okay, so okay. So I'm finding out that this program does not draw straight lines, which is really annoying, but that's okay. So this, let's see. So there's a scale on the right hand side that kind of shows what the approximate stability is of the kind of like coloration of this band here. And it does not look very good to me. It's probably just in the file transfer. This has gotten a little weird, but basically what I see when I'm looking at this is this might be on the very, very margins of this band of stability. But I'm going to say it probably would fall maybe just outside of it, but not entirely sure. I'm actually going to look up the answer key because that is a really fringe case. Yeah, so this is listed as not being a stable compound. So, what that means is that this, so this is not stable, and pretty clearly, from where this falls on the graph, it would be more stable if, or stable at all, if this were to have either more neutrons or fewer protons. And so the easiest way to do this, to go like, essentially the easiest way to move an isotope to the left on this graph and to get it closer to this band of stability, which is along there. That was really badly drawn. Please just pretend I didn't do that. So if we want to move left, we undergo alpha decay. An alpha particle. So now we have to talk very, very briefly about the different kinds of radioactive decay. So there's alpha, there's beta, there's gamma. There's beta plus and there's beta minus. That's all I can think of right now, so we're gonna roll with that. So alpha decay is the loss of 4,2-He. So alpha decay is effectively the loss of a helium nucleus. And what this is two protons and two neutrons get together and they piss off. So if a bismuth 186 nucleus undergoes alpha decay, then it will turn into a 182 81. Can't think of what an 81 is because I don't know the whole thing. Thallium. So it would turn into a nucleus of thallium. TL. That's an L, trust me. And so having 101 and 81 versus 103 and 83 would take this just a little bit down this way. and so it gets it closer to the band of stability. It's not necessary that this decay produces a stable isotope, because this could be one step in a series of radioactive decays, and so that may draw it closer to the band of stability until you reach a stable isotope. Because lots of these have, a decay series that are, even up to like a dozen steps long. There's no requirement that the product be a stable isotope itself. And thank you so much, Cheesiest for Cakes and Math Mackie, for the follows. Really appreciate that. Welcome in. Okay. So I'm not concerned with going down the entire radioactive series, because that's not what the question is asking for. Let's see. Jesus for Cakes. I have minimal experience with chemistry, but this looks awesome. Well, thank you so much. I'm so excited that you're here. So let me tell you just a tiny little plug for what this is. I am about 90% of a PhD. I just have a little bit more writing to do, and then my thesis, and then I'm done. So I've been doing this for a lot of years, and I really like the idea that knowledge should be free. And so I just want to come in and talk about nerdy stuff that I enjoy. And this is going to be a little bit aimed at people who are taking chemistry, but I want very much to make this accessible for anybody to just drop in and learn some stuff and see how chemistry gets done, and just talk a bit about like how I approach these questions and give a little bit of an explanation as to what's going on. Congrats, I'm still in high school. Should be taking chem in the summer. That's fantastic. Taking chem in the summer. So like, does that mean like, are you going into university soon, or are you still going to be in high school for a bit? Because chemistry, I feel gets a little bit of a bad rep because it's really hard sometimes, and it is not a lot of people's cup of tea, and so I've done a lot of teaching, I've done a lot of tutoring, so I've found like a little bit of a, I have to do this, and it's hard, but like. I think that this stuff can be really fun, really interesting if it's, approached in that sort of way. But, all right, I'm still going to be in high school for a bit, but I'm taking dual enrollment since I really like fusion. Oh my God. I could talk for a long time about fusion. Because fusion, you have hit upon one of my hobby interests, one of my little autistic special interests. So I think fusion is incredibly exciting, really interesting stuff, and the advancement of people's understanding about it and the technology is absolutely spectacular. So I love that. Hear a lot about chem, but hopefully it's better than physics. I love physics, but it's made me cry a few times. Yeah, hey, same here. And it's because like I find like the math is tough. Me and math we've got a good understanding going, because I love math, I respect it, but we are never going to be good friends. Oh my God, thank you so much. You're so kind. So like physics is very math heavy, and again, like I love physics, really cool. I'm not great at it though. So, but like, yeah, I've got a broad range of interests, so I will probably rabbit trail into all sorts of stuff, given enough time. Fusion will definitely be one of those. I would love to talk more about that sometime. But like astrophysics, cosmology, all that stuff, I find it deeply fascinating. So yeah, same. I mean, when I was in high school, fusion was just a pipe dream. The saying was always, fusion is 30 years away, and it always will be. But that's not the case anymore. We're really getting there, and it's fantastic. So, I want to get to Felipe's question. Are you able to do 19B for that practice test when you get a chance? Absolutely, my man. I will get right on that. So yeah, so this is right. Okay, let's get to it. I want to very quickly finish up what I'm talking about here, and just show where this titanium 60 falls on this graph, and where that gets to. So, we got a total mass of 60. We've got 22 protons in the titanium nucleus. So we're talking about right here, and we're talking about 38 neutrons, which is here. So this is going to be also outside of the band of stability. But this one needs to go to the right in order to get closer to that stable that stable isotope. So to go to the right on this table, we undergo beta minus decay. And so beta minus decay is trying to think. All right. Okay. One second. I want to deal with this comment. I really like thorium energy and bismuth 213. I think couldn't tell you off the top of my head, but it sounds about right. Very well over all the specifics. Yeah, like thorium energy in particular. These thorium like the molten salt reactors. Absolutely fascinating. It's puzzling to me that did not become the major source of nuclear fission energy. But there's probably a lot of political issues with that, because thorium reactors don't produce plutonium, and so you can't make weapons out of them. So a lot of governments weren't interested. But there's other reasons as well. A lot of engineering issues with molten salt reactors. But okay, let's keep doing this. So we're talking about beta minus decay, and so that is. Okay. So one thing that I should make very clear is, like, yes, I'm pretty good at this chemistry stuff. I've been doing it a long time, but I promise you, I will not know everything off the top of my head. And this is one of them. I don't remember what beta minus decay, what that entails. Okay. So beta minus, a neutron is transformed to yield a proton, causing an increase in the atom's atomic number. How lovely. That was the wrong button to press entirely. All right, let's try again. Very good. Okay, neutron is transformed to a proton. So what that would look like is, so if a neutron is transformed into a proton, there is no change in the total mass. So we're like it is not going to be titanium. Careful. So neutron is going to be 0, and it's going to be +1. And let's just call that element X. So this is going to be what that looks like. So a neutron being turned into a proton does not affect the total mass, because neutrons and protons weigh essentially the same amount, but the number of protons is going to increase. So we're going to stay at 60, and then the atomic number will increase to 23, and that's going to take us from titanium to vanadium. Boop. Boop, boop. Very, very good. Okay, and yeah, so that brings this element a little bit to the right, closer to the band of stability. Again, this need not be a stable isotope. It may just be kind of on the staircase of radioactive decay. But we'll leave that one there for now, because Felipe would like to go over 19B. So let's get to that. Alrighty. Okay, so start with A. Why is hydrogen the only neutral atom for which the ionization energy can be readily calculated? That is God. Felipe, you got to make me actually think about this. Come on, dude. No, okay, it's fine. Okay, so. So there is the issue with calculating ionization energies is that if you have more than one electron, then you've got a multivariate system, which is to say that there's forces between the nucleus and one particular electron, and there's forces between the other electrons and your kind of electron of interest. And so this is actually plays into, if you've seen on Netflix, the three-body problem. This is a problem. Essentially, this is a problem with math, because when we have multiple variables that each affect each other, then we have to make approximations to remove variables before we can solve for just one of them. So this is why hydrogen having, being neutral when it has exactly one electron, it's just a two-body system. It's a proton and an electron. So that's a simple system. We can very precisely calculate that. Hello, my little love. Everybody, meet Daphne. This is my cute little floofums. And when she comes up here, frankly, she takes priority because she's cuter than all of you, because I can't see you. But she's lovely. And if you want to know why I'm called Dr. Beans, this is why. Look at them beans. They are glorious. And this is my very precious kiddo. Hi. Yeah, who wants to get away now? Yeah. Oh, you so good. Please don't sit on my keyboard. That will go poorly. All right, you are so good. All right, we'll see if the other floofs come around at any point, because I've got two catos and a pupper. that is correct. She is adorable and much cooler than I will ever be. Okay, so I can't remember where I left off. I think I explained why you can only do it for hydrogen, because as soon as you get to like helium, you've got three bodies. You've got the nucleus. It's got two protons, but you can treat the nucleus as one entity because they're not moving relative to each other. Hello. But it has two electrons. And so it becomes impossible to calculate precisely. But it'll be interesting to see if at any point, like given the kind of advent of quantum computing and the kind of lifting restrictions of things being either 1 or 0, if we'll be able to generate some new maths that can explain three-body problems. But we, as far as I'm aware, are not there yet. So calculate. So this is where Felipe wanted to get to, which is calculate the ionization energy of a neutral ground state hydrogen atom. All right. Super don't remember the formula for that, so we're gonna look at some stuff. Okay. Right. Okay. So that's it. So the equation that we're going to be working with is so E I equals E N equals infinity minus, and I will explain what these mean in just a moment. Okay, so this is going to be yes, you're right. It is the Rydberg constant. So EI equals EN minus EN equals 1. So what we're talking about here, I'm going to actually make this a little more clear because I did not write that very well because I'm a messy boy. So EI. So this is an ionization energy. And so what that is it's the amount of energy that is required to dissociate an electron from its nucleus. So there's lots of different energy levels that electrons can occupy while remaining associated with the nucleus. You can get it into excited states that are like higher energy or more reactive, and there's lots of applications in chemistry for that. But here we're talking about ionization energies. We're talking about removing an electron from the element entirely. And so how we set this up is as En equals infinity. What that means is that this is the energy level of an electron that is no longer associated with the element. So let's talk a bit about energy levels in an atom. All right, that'll make sense in a minute, promise. Well, probably. Okay, so what this is saying is the infinite energy level, which is dissociated from the atom, the electron dissociating from the atom, minus En equals 1. And n equals 1 is the ground state. So this is just, for a hydrogen atom that just has one electron, it would look like this. It is the lowest energy level that an electron can occupy in this particular element. And we can go up. I don't know if you can hear my dog barking outside, but well, I don't know where I was going with that. It's a thing that's happening. But sorry. Not ADHD, you are. You're the one getting distracted, not me. Yes, it is me, actually. Okay, so these are all different energy levels that that an electron can occupy while remaining associated with the atom. N equals infinity, or close enough. So if the atom, if this neutral hydrogen atom were to absorb an amount of energy that corresponds to this distance, the energy gap between the ground state and the first excited state, n equals 1 and n equals 2. So if the atom absorbs a photon of this energy, then what you'll have is it will end up being in n equals 2 in the first excited state. If it absorbs a photon that has exactly this much energy, because this is all working on quantum systems, so we have to absorb the same amount of energy as the energy gap between these levels. So if it absorbs a photon of that much energy, then you excite the electron up to n equals 3. And these energy levels, as you go higher and higher, they get closer and closer together. There's reasons for that I will not get into because it's just not super relevant. But suffice it to say, there's effectively an unknown number of energy levels, but just take it to be a lot. But at some point, you can get to an energy level, you can get to a point where the electron has so much energy. It's been excited to such a high state that it is no longer associated. It does not stay with its nucleus. Instead, it just flies off into whatever. And this is when it has reached this threshold of n equals infinity. So this is when it becomes ionized and leaves behind a charged nucleus because it's lost an electron, which carries a negative charge. Okay, so that's a little bit of a primer on what this equation is talking about. And so what we have to do is, so we're trying to calculate EI, the ionization energy, and so we have to, I want to put these in brackets because that's a little confusing to me. Okay, so we have to take that E equals, or sorry, the E of the infinity energy level minus the ground state energy. So so this is going to look a little bit strange, but I promise I will explain it. So the energy of this n equals infinity is 0. And yes, that sounds weird because an electron would have to absorb a certain amount of energy, a non-zero amount of energy, to get to this this threshold, to get to the ionization energy. But this is okay because we're not talking about an electron in this energy level has no energy. That's not what we're saying. What we're saying is that we've set this energy level, this ionization energy level, to 0 joules. And the ground state is set to some energy that is negative. Negative E n equals 1. So the energy of the ground state here is denoted as a negative energy, which then we can because we've set this term to 0, we can set the ground state energy to a negative. So question, so is the ionization energy like the magnitude of the ionizing radiation? That is a very good question. So let me think about how I want to answer this. So I want to be careful with my terms. Magnitude of the ionizing radiation. I guess my short answer is not necessarily. So it's related to that. The ionizing radiation must be at least this amount of energy. But once it has gotten to at least that much energy, it can be any amount of energy higher than that as well. Because essentially, there's, you get up to, the energy level that will put you at n equals infinity, and then there's, an infinite number of energy levels above that threshold that the electron can occupy. So the ionizing radiation that hits it, that promotes that excites the electron, must be at least that much energy, but it could be any amount more as well. Let me know if that answers that question, because that's something I can definitely get into more if needed. Okay, so the En equals infinity is just set to 0, and then the En equals 1. So this is equal to the Rydberg constant times z squared over n squared. So this is what the breakdown of this is this is once again number of protons, and then the n here is the same as this n. So here we're looking at like what is the energy of the ground state energy level, and so I don't know where I was going with this sentence. I'm going to start again. So when we're looking at the ground state, we're looking at the energy level number one, the first one, and so it is that one that gets substituted in here. So this equals the Rydberg constant times 1 squared over 1 squared, which is, like, both of these terms are just 1, so it's Rydberg's constant times 1 over 1, Rydberg's constant times 1. It's just the Rydberg's constant, which is 2.179872, because I happen to have that up, times 10 to the minus 18 joules. All right. I'm missing something. This. Okay, so this is supposed to be a negative number. All right, I have seen your question, cheesiest of cakes. I will get there momentarily, I do promise. So, yeah, so this is negative RH times Z squared over N squared. Z squared, number of protons, 1 squared, the identity of the energy level. Rydberg's constant equals that. So this would be, minus negative 2.1798 so and so. So this would just equal 2.179872 times 10 to the minus 18 joules. That is, if you can read that, well done. Okay, so this is how you'd calculate the ionization energy of the ground state hydrogen atom. I can talk. Words are hard sometimes, though. Okay. Okay, so let's deal with this question. So you half get it. As n increases, does the radiation also increase, or is it like a car tank where there's a threshold? As n increases, so as the energy level increases, does the radiation also increase? So, if I'm understanding correctly, I think my answer would be kind of. Okay, so okay, so if we had an electron that was in n equals 3, for example. So here's the just the continuation of, there's the ionization threshold. EI, very good. So if we've got an electron in the n equals 3 energy level, it would be correct to say that electron could be ionized by the input of a smaller amount, or by a lower energy photon, because like it's got less distance to go to get to that threshold, right? Because it's already in an excited state, so it's got more energy than an electron in the ground state would have. So it wouldn't take as much energy to ionize that electron. So in that sense, this is like, yeah, it would take it wouldn't take as much to ionize an electron from the n equals 3 energy level compared to n equals 1. But there's an equation called the Boltzmann distribution, and cat, y'all should just see this, because Daphne is now laying on top of my computer, which is very cute, but no, please, hi, I love you very much. Please don't do that. Oh gosh. Okay, so basically the concept is that if you've got a sample of this compound, and you are bombarding it with radiation, like let's say, yes, there was a wild cat has appeared. So if you've got a whole sample of whatever this happens to be, whether it's hydrogen, whether it's something else, if you're bombarding it with radiation that is at exactly this energy, the energy difference between n equals 1 and n equals 3. So you're taking and you're exciting a bunch of electrons into the n equals 3 energy level. But the question is, like, how many of the like individual atoms of this material do you think have this excited electron? And even if you are bombarding it with, like, if you've got like a lamp that is just like shining on this material in a petri dish, a really small percentage of the atoms will actually absorb that energy and have an excited electron. So, and of course, like this absolutely depends on the intensity of the light source, how many photons of that energy are being produced and bombarding the sample. But even with a pretty good source, like a light source that is efficiently bombarding it with exactly this energy of light, you'll have probably at least 98+% of it will be in the ground state at any given time, because it is a small proportion of the atoms of this will absorb that radiation and excite the electron. And when this happens, the reverse will also happen. You will relax from the n equals 3 energy level down to the ground state again, and this is extremely fast. So at any given time, while this sample is being bombarded, it's a very small proportion of atoms of this that will have an electron in this n equals 3 energy level. So the chance of, like, if you were bombarding it with this amount of light as well, you wouldn't get a whole lot of ionization from the n equals 3 energy level to the ionization energy. So the lamp and the n equals 3 versus n equals 1, is it closer to, the closer it is to the minimum, the more likely it is to radiate, rather than black and white case. And please never apologize for asking questions. I love questions so much. I adore them. I think questions are always very welcome. Also, because I'm a very neurospicy individual, and so I am always willing to rabbit trail and be distracted. So it's closer to the minimum. The minimum, the more likely it is to, I guess, radiate rather than a black and white case. So I I think I get what you're getting at, and I think the answer is yes. So like, if you had, okay, so let's take this example, and let's say you've got three sources of light. So you've got this one is source one. Uh, this one is source two, and let's call red. Let's call red being source three. Okay, so source one. I don't know why I'm physically pointing at the screen. That doesn't do any good. You can't see that. Okay, so source one will excite an electron from the ground state to the third energy level, n equals 3. And that's all it will do. It'll go up, it'll come back, and it just go back and forth forever. Light source 2 would be absorbed by any electron in the n equals 3 energy level and ionize it. And then light source 3 will be absorbed by a ground state electron and it will ionize that. And in this type of situation, I'm sure that you would get some proportion of these comments that would be ionized by light source 2, because it would, just by probability, that at some point when it's being bombarded with light source 2, you would have an electron in the third energy level, and that would catch that photon, get excited, and be ionized. That, I'm sure that would happen. But the vast majority of the ionizations that you would see in this case would be from light source 3, ionizing electrons directly from the ground state and taking them to that ionization threshold. So that would be by far the largest source of ionized electrons. I hope that answers your question. Let me know. I'm going to keep going through this for a minute. Okay. So the third part of this, question C, is just converting joules to kilojoules per mole. That's kind of just a conversion. I'm not going to worry about it too much, but you would essentially take this number divided by 1,000 would equal the kilojoules, and then you would so if you got that, then you multiply that number by Avogadro's number, which is a conversion from a thing into a mole of a thing, and the units of Avogadro's number are what is it, a 6.022 times 10 to the 23 mole to the negative 1. So yeah, you multiply it by Avogadro's number, and you'd get units of kilojoule per mole. 23. Yeah. Pretty sure. This is sounding weird to me for some reason. Per mole. Anyways, okay. So, cheesecake, why would it affect the ground state more? Is the ground state more unstable, or is it constant throughout? Okay, no, that's fine. I see what you're getting at. So it would affect the ground state more because almost all of the electrons are in the ground state at any given time, even when it's being bombarded by that radiation that excites it to the n equals 3 energy level. Almost all of the electrons are going to be in the ground state, and so it is. It's just a matter of like how many electrons do you have in the ground state versus how many electrons do you have in the excited state. and the number of electrons in the excited state at any given time is extremely small. So the ground state is more affected because there's more electrons in that state. It's not at all that the ground state is less stable. It is in fact, it is absolutely the most stable. The ground state is the lowest energy state, which is the same as saying it's the most stable that it can be. So yeah, hope that clears that one up a little bit. But yeah, so it's very much the case that like the ground state is the most stable, but it's also the most populated by a large margin. Okay. All right, so calculate the longest wavelength of light that can be used to ionize a hydrogen atom. I love this question because this is going to illustrate the relationship between the wavelength or frequency of light to its energy. So the energy is 2.179872 times 10 to the minus 18 joules. Okay, so again, this is the ionization energy for an electron in a hydrogen atom. So what we need to do is find what frequency of photon would have this much energy. So we need, what is it? E equals h nu. H nu. There we go. So it's not a V. It is the Greek letter nu, and h is Planck's constant, and this relates the energy contained in a photon to its frequency. Just want to make sure that I've got that right. Okay. Okay. All right. So we're going to use another equation as well. So this denotes the frequency of the wavelength, but we want the answer. That's how English works. This is the frequency of the photon, but we're asked to do it in wavelength. So we're going to take a little bit of a shortcut and use the C equals lambda nu, which relates the speed of light to the product of the wavelength of a photon multiplied by the frequency of a photon. And we can rearrange this. So if we divide both sides of this by lambda, then we cancel out this lambda, and we're left with frequency equals c over lambda. So speed of light over the wavelength gives you the frequency of a photon. And so we're going to say that so this frequency is, we're just going to replace that term. So it's going to become E equals hc over lambda. So now we've got the equation that we're going to use, and so we take this number, and that is our E. So just directly plugging this in, this is the energy that we want. This is the energy of a photon that would ionize that electron from a hydrogen atom. H is Planck's constant. C is the speed of light, which is also a constant. So our only variable here is lambda. So if we rearrange this again by... First we multiply both sides by lambda. So now we're canceling that lambda. And then we've got lambda E equals HC. And then we are going to divide both sides by E. And that gives us, because these E's cancel, so it gives us lambda equals HC over E. Going to make me do math, are ya? All right. All right. I don't know Planck's constant off the top of my head. Let's see. Planck's constant. 6.626 times 10 to blah, 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 blah. Okay, so lambda equals 6.626. There's more numbers, but I'm going to ignore them because they won't matter much. 10 to the minus 34 joules times hertz to the minus 1, so joules per hertz if you prefer, multiplied by the speed of light in a vacuum, of course, by 2.977 times, sorry, that is 2.997, 8, fine, whatever, times 10 to the 8 meters times seconds to the minus 1, which is the same as saying meters per second. All of this being over the thing that I really don't feel like writing again, but I'm going to anyways. 987 times 10 to the minus 18 joules. I know I left a number off of there, but it's a very, very small number, and I don't care. Okay, I'm going to take a moment to answer your question. Also, if it is bouncing indefinitely from n1, n equals 1 and n equals c, how come the density of the electrons are different? I want to be careful with my terms here. So electron density is a specific thing talking about like how many electrons occupy a certain space. What I'm talking about in this problem is the population, the ratio of electrons that are occupying the ground state compared to the number of electrons that are in the excited state. So so it's just saying like in that sample, even while it's being bombarded by that light, probably 99+% of the atoms, of the electrons, I should say, are going to be in the ground state. Just because these absorption events are just less frequent than you may imagine, and there's like very quick processes that oscillate between absorption and emission, right? Because when an electron falls from the n equals 3 energy state back to the n equals 1 energy state, it releases all the energy that it absorbed to get to that n equals 3 energy level. So it's merely a matter of when this sample of millions and millions and millions of these atoms are being bombarded with the light, there's only a few that are going to absorb that energy to excite the electron into n equals 3. N runs to n equal 1 but walks to n equals 3. I think I do like that terminology. I think the nuance is not quite going to correspond to that, because these processes happen at effectively the same speed. Like there's not really any significant like time delay in this process occurring, but for how should I say this? I'm trying to think of a different analogy, but it's not coming. Okay, I think that's a pretty good way to think about it. Runs to n equals 1, but walks to n equals 3. I don't mind that at all. I want to be careful to state that that's not quite the reality of it. But it is a good way to think about it, because that's kind of how you might get to this conclusion of the different populations of the ground state versus the excited state. So yeah, I do like that. So that's if that's a helpful thing for you, if that makes your brain feel good, that's perfectly good. Yeah. Okay. So to finish this off, I'm going to get my very, very fancy calculator out. So it's going to be 6.6. Would this be? How do we do this? 10x? Nope. Not that. Go back. Hate it. Piss off. Okay, so 10 to the negative. Hey. Okay, so 6.6 times 10 to the negative 34. Good lord, that's hard to. Oh, can we just do this? Maybe. Anyways, so multiply that by 8. Okay, so that's what we got. And then dividing that by 2.1797 times 10 to the negative 18. So it gives us a wavelength. Okay, so one thing that is extremely important in chemistry is unit analysis. So tracking your units as you go through these equations. This is so incredibly important. If you're practicing this stuff, I don't bother practicing getting the numbers right. Numbers are easy. It's units. Track your units very carefully. So when we're going through this, so we've got joules divided by joules. So those cancel out. And now we've got hertz times meters per second. And hertz are in units of seconds to the minus 1. Sorry. So yeah, hertz are in units of per second. So it's something happens this many times per second, and that's hertz. Like our alternating current power grid, at least in North America, is set at 60 hertz. So it cycles backwards and forwards 60 times per second. Okay, so we got second, 1, 2, 6, 1. How do I actually screw this all up? 19. Doot. 2 is per hertz. Oh, that's why. Yeah, okay. Sorry. Got a little confused for a second, but we're good. So, hertz to the minus 1 equals 1 over seconds to the minus 1, and that just equals seconds. So what this works out to, so hertz to the minus 1 is equal to seconds, and so that actually cancels out. So hertz cancels out. Hertz to the minus 1 cancels out with seconds to the minus 1, and then we get a bunch of this. So 9.11, call it 3 times 10 to the minus 8 meters. Felipe, my good sir. Use E equals H nu to find nu, and then use C equals lambda V nu to find the wavelength. Just wondering why you did HC over lambda. So it's just kind of condensing my steps here. Because the way that you did it, perfectly valid. Absolutely no issues. But I just... basically, I took that C equals lambda times nu to rearrange it so that I could call nu in the E equals H nu. I could just call that C over lambda, and it means the same thing. Like because I changed this equation into this form, it means I can substitute the nu for just C over lambda because it equals the same thing. So I'm just doing in one step what you're doing in two, but absolutely equally valid ways to tackle this. So this would be 91.13 nanometers if my mental math is working okay. I'm pretty sure it is because I do it a lot. So yeah, and I should actually show what I'm doing though. Nanometers equals 1 meter over 1 times 10 to the 9 nanometers. So I don't know why I put that there. That's silly. It doesn't belong. So basically, I could say this. So this many meters times 1 times 10 to the 9 nanometers over a meter. The meters will cancel, and then the units that we're left with are nanometers. All right, and so that does it for that one. Felipe, is there any other questions on this practice test that you'd like to go over specifically? Because I feel my brain starting to get a little bit fried. But I am up for going for a little bit longer. All right. That's a cool one. You okay? Very good. All right. So Felipe's got a final exam on this stuff tomorrow. So Felipe, good luck, my man. I know you've worked really, really hard this semester. I am super proud of you. You should be super proud of you. And you're gonna nail it tomorrow. I believe in you. All right. I think my brain is actually just about had it. So yeah, Felipe, if you're good, I'm gonna sign off in a little bit here. Cause like I said, chemistry's hard. It's a lot of brain work, and it is it's tough to do it for whoa, all right, for long stretches of time. Because the brain do fry a little bit. But yeah, so I'm going to sign off pretty quick here. Cheesy Stuff Cakes, I super appreciate you coming in and chatting. I would love to see you again. I'm going to be doing this every Tuesday and Friday, 7 p.m. You can find me here. I upload all of these to my YouTube channel as well of the same name. But yeah, would love to see you back anytime, and yeah, bring all those questions, because questions are just absolutely fabulous. Cannot tell you how much I love them. Time zone is Mountain Time. I'm in Alberta, so yeah, Mountain. I can't remember if we're on daylight time or because daylight savings time is frankly stupid. But yeah. Mountain Time. All right. Perfect. And that is something I don't need to do right now. All right. Okay, sorry, new obsession. Here I come. Hell yes, we love it. Yeah, I think chemistry is pretty cool. There's a lot of stuff that's just I love to know the reason why things happen, and chemistry is really good for like kind of getting to the nitpicky bits of that. And there's a lot of fun stuff to do in chemistry, particularly like, if you are working in a lab. I've been like doing research and working in labs for I think about 10 years now. I mean, it'll get you hooked because you put some stuff into some other stuff and something else comes out, and sometimes you get to make things all flamey. Sometime I'll tell you about the time that I turned a flask into a flamethrower because I mixed two things that I was told you should not mix, but I wanted to see what would happen. I think pretty much every chemistry major has like at least just a little bit of pyromaniac in them. I am no exception. Yeah, so there's lots of fun, extremely dangerous stuff that I've had the privilege to play with. But yeah. Yeah. So yeah, super appreciate you coming out. Would love to see you again. Yeah, until next time, you all take care and yeah, be safe out there. Bye.